All right, in the last video, we did an ideal gas law application, solving for density. You're going to want to know how to do that one. Yes, you are. Our next academic adventure will be problem solving heavy. And if we had met tonight on campus, we would have gone through this bad Larry right here. Ooh, this one. This bad Larry right here, which I loaded into Canvas for you. And if you haven't gotten it, go get it now. We'll wait. You're going to need it. Come on. Go get it. Download it. Okay. Okay, got it? Okay, good. We're going to go through each and every one of these problems this evening. Problem-solving heavy night would have been the most problem-solving heavy night of the semester. So we're going to need to know how to do 1, 2, 3, 4, 5, 6, 7, 8 problems, and you will need to know how to do them. Your next academic adventure will consist of 11 problems to solve. 8 of them from this piece of paper. What about the other 3? Good question. Last time, it would have been last week had we had met. The last video was using the ideal gas law to solve for density. You're going to have to know how to do that one. 2 others come from basic gas laws, cross, multiply, and divide. Make sure everything in Kelvin. And you'll have 2 problems using those cross, multiply, and divide basic gas laws. Okay, let's dive into problem number 1. Problem number 1. Gas stoichiometry. Must have something to do with gas. Must have something to do with stoichiometry. Oh, good name. This problem says, use the following equation, and given 50 grams of the nitrogen monoxide, how many liters of the nitrogen dioxide could you make? You see the difference here? We haven't never done one like this before. We have to go from grams to liters. Exactly. New problem. What we need to do is combine stoichiometry, 50 grams, to find product, and how many liters. That's going to use a gas law. Which one? I'm dealing. Ideal gas law. All right. Let's dive in here. You've got 50 grams of the nitrogen monoxide. Multiply, divide. Stoichiometry. It doesn't go away, people. It doesn't go away. Grams of nitrogen monoxide on the bottom. You have to go to moles on the top. Grams to moles, moles to grams, the most important thing in all of chemistry. 1, please never forget it. Okay, so go to 1 mole. Grams to moles, we always put a 1 next to the mole. Add up nitrogen. Let's see. Nitrogen, that's 14, and oxygen, 16, 14, and 16, 30. Okay, so we get 30 grams per mole. Now, this is only going to solve for moles of nitrogen monoxide. I don't want moles of nitrogen monoxide. I want moles of nitrogen dioxide. So I'm not done. Now, actually, at this point, some of you might be saying, well, why do you want moles of nitrogen dioxide? How do you know that? Well, 1, I made the problem up, so that's how I know it. The other way I know it is because we're going to need to figure out the liters of the gas. So we need the ideal gas law to do that. And the ideal gas law, if we all remember, has moles in it and is moles. So if I can get the moles of how much of this stuff can be produced, I can use that in the ideal gas law. Solve for volume, liters, volume. All right, that's why we're trying to figure out the moles of the nitrogen dioxide, because I can put that in the ideal gas law. Okay. So moles on the top, moles goes on the bottom. Bells / whistles and or whatever are going off in your head right now. They should be. Because you have, for the first time in the stoichiometry calculation, moles. That is a mole retile. Retile. A nice Irish word. Yeah, sounds Irish. So moles goes on the bottom. That's a mole ratio. So I'm going to put moles of, well, whatever I want. It's America. Whatever you want up there. Don't let anybody tell you what you can and can't do. But I do want to get the problem done sometime today. So let's put moles of what we're trying to find. NO2. NO2. Okay. We all remember that from the mole ratio. The coefficients are my numbers. 2, 2. Sweet. Cancel out. Do the math. 50 divided by 30. So this is 50 on the top, 30 on the bottom. 50 divided by 30. What does that come out to be? let's see, 260, 230. 1 point evil. Evil, yes. 1 point evil. I know you're thinking, what the heck are you talking about, Willis? That's 1.666. Get it? Funny. So we'll round it to 1.67 moles of the NO2 produced. Okay, so what do we do now? Well, remember, the original question is to try to figure out the amount of liters. So the amount of liters is going to be used, we're going to figure it out by using the ideal gas law. So now let's plug the ideal gas law in. Well, actually, let's put it up here and then we'll plug stuff into it. So let's go ahead, write that down. So PV equals nRT. You want me to figure out volume, the liters. So that's unknown. So in order to get V, I'll divide nRT by P. If I have all this stuff, I'm golden. I'm like Pony Boy. Stay golden, Pony Boy. Stay golden, Pony Boy. Okay. So N, we just figured that out. That's 1.67. 1.67. And that's moles. I'm just not going to write the units on. Save me some time and marker. Ooh. All right. R. You have 3 choices, Padawan. 3 choices. Choose wisely, Padawan. Well, it's going to depend what the pressure is. They didn't give me the pressure. Oh, yes, they did. Well, they didn't. I don't see a number there. They gave it to you in STP, standard temperature and pressure. Now, you, STP, standard temperature and pressure, being the American that you are, have a choice of which pressure you want to use. You can use any pressure you want as long as it's standard. Standard pressures. 1 atmosphere, 760 millimeters of mercury, 101.3 kilopascals. You can use any one you want. Choose. Susan, which one do you want to use? I want to go with atmospheres. It's easy. It's a 1. Very good, Susan. Very good. Let's do that. Let's use 1 atmosphere for our pressure. Certainly makes the math easier. Now the R value has to be the corresponding R value for 1 atmosphere, which we all remember is 0.0821. Okay, 0.0821. Okay, standard temperature and pressure. Temperature, standard temperature. Standard temperature is 0 degrees Celsius. Standard temperature is 0 degrees Celsius. It wouldn't be a pleasant 0. I mean, if you had your lab at 0 degrees, it'd be kind of cold. It'd be all chilly and whatnot. A little bit chilly. You'll be a little vegetarian chili. Go vegetarian. Best. Okay, now, 0 degrees Celsius. We're going to put that right up here and multiply through. And you'll get 0 on top. And that doesn't make any sense. It shouldn't. We don't use Celsius. Kelvin, Kelvin, Kelvin. So 0 plus 273, 273. So 273 is my standard temperature. Now I do the math on this. Okay, let's see, do the math. Let's get rid of this. Okay, clean this up a little bit and do the math. And what we hope is we come out with the answer that I gave you right there on the answer sheet. Okay, let's see if we do. Okay, let's see. 1.67 times 0.0821 times 273 equals 37.4. 37.4, please, 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 please. Yes! Happy dance. All right, nailed it. All right, we got it right, 37.4. And the answer will be in liters. Liters is going to be our basic unit of volume with our ideal gas law because the constants have liters in them, that's why. All right, so now we got that problem solved. We'll stop this video. Whew. I'm going to go have a stiff drink or something like that.